Right. Yeah, Yi Chen should be here, and Jake Woosley. Yi Chen should be here. Woosley should be here. And that, yes. And that adds up to 8. So those 2 are the ones, I don't know where they are. For those of you on Zoom, oh, here's someone else. We only have 2 people in class, now 3. So
Am I part of that?
no, I'm saying just in the classroom.
Oh, I see.
It's just very empty in the classroom today. Okay. Well, let's get started anyway and hope that Jake Woosley shows up soon. Oh, he's on. Okay, good. Good. Okay. So I realize there's still a bit more of kind of the math stuff that I wanted to talk about before we get back really to the punchline in section 3.2, which is talking about why we're defining Hermitian operators and why we're so concerned with Hermitian operators, and we'll certainly play with that definition. But so far in our description, we've been talking about vector spaces and what makes nice structures on vector spaces. We want inner products and norms to do the kind of stuff we're going to be doing in quantum mechanics. And we also talked about we would want our vector space to be complete. We talked about that last time. And if it's complete, it has an inner product and it has a norm derived from the inner product, then we call that a Hilbert space. And the upshot is Hilbert spaces are just the nicest kind of spaces of vectors. A lot of times we'll think of them as functions, the vectors as functions that you can deal with. There's a lot of less nice ones, but we're not going to have to worry about the problems. Take a graduate course in functional analysis. You'll learn about all the problems that can happen if you're not in a Hilbert space. But we haven't talked about operators, right? We bothered to define the momentum operator, the Hamiltonian or energy operator, the position operator back in chapter 1. And so we're going to be concerned with operators, and we want to think about, we're talking about a vector space. You all have a certain idea about operators on vector spaces that you've done before, and we want to connect with that, but generalize to the notion of spaces of functions as being vector spaces. So we're going to be talking exclusively in quantum mechanics about linear operators, and we're always going to denote linear operators by a symbol with a hat over the top of it. And I guess I should say up front, that hat has nothing to do with unit vectors, right? This is not a vector. It's just a different or similar notation for something that means totally different. Hat means operator, and a linear operator is a special kind of operator that kind of distributes over linear combinations of vectors. So here in parentheses, a arbitrary linear combination of 2 vectors. The linear operator can distribute right through it. So just to give an example of that on the board here, you're already familiar with linear operators. Let's see, why is this so far out of focus? Is it going to do it automatically? No, it's not. That's not good. Hopefully it can autofocus because I don't have the software installed to manually focus it, I don't think, on this computer. What is going on? Can I move it to the point where it gets more in focus? Let's try that. Still no? Yeah, I'm assuming that means just unplug the USB and plug it back in. Oh, you mean just switch cameras for a second? Yeah, just stop the video and restart the video. Yes, now it seems to be in focus. Let me back up. Sorry, guys. I thought I looked at this earlier and it was totally in focus, but somehow it got phased in the middle.
Well,
So-
it seems to be working now.
Yes, it's nice and in focus now. So Yichen just said, stop it and start it again, and that usually fixes it, and it did. So, we've been talking about operators that on our vectors we've been thinking of might be represented by functions of x, right? And if we have a function of x, operators might be things like derivatives. So a derivative operator is like this, and this is an example of a linear operator, right? This is with an minus I h bar out in front, that would make the momentum operator. So this is almost the momentum operator. You're familiar with the fact that if I have a constant times one function of x plus another constant times another function of x, without even thinking about it, I distribute it across this and write it as a times d dx of f of x plus b times d dx of g of x. That's the kind of stuff you do all day long in calculus, right? So derivative operators, first derivative, second derivatives are certainly linear operators. The position operator, which means multiply by x, is clearly a linear operator, right? If I multiply by x out here, I can move the x in there and there next to those functions. So you have lots of examples of linear operators. Okay. What do linear operators look like when we're talking about these different representations? Well, we just talked about some examples when our representation of vectors is functions of x. What about in our good old friend finite dimensional vector spaces? That's like our C2 or C3 or R3, the space of three-dimensional vectors that you're familiar with from Physics 210. As you probably know, linear operators correspond to matrix multiplication of the vector by a matrix. So if you're on a two-dimensional vector space, it would look like this. In abstract notation, here's my operator operating on some vector, and what it does is transform it into another vector. So I think of the operator transforms this vector alpha into a vector beta. Now that's very abstract notation. To be more concrete, I might say, well, I'm going to represent these vectors in the usual way by column vectors of their components in a particular basis, right? So the usual way. And what this operation looks like explicitly in terms of components is there's a matrix that represents that operator T in that particular basis. And we do the usual matrix multiplication. I guess I should remind you of a couple of things, right? That these, I'm denoting the matrix elements by Tij. Remember, the first subscript index is always row, and the second one always column. We always go row, then column when you're writing down indices like this. So this T12 up here is in the first row, second column. Right? That should make sense in terms of it, right? And we know how to do matrix multiplication, right? You probably remember the process, right? I always say it like this. To get this top position here, the first row of the resulting vector, I take the whole first row and multiply by the first column here. And there's only one column to multiply by there. And when I say multiply, I mean multiply the first elements and then add that to the multiplication of the second elements. So row times column. First row, first column gives me the first row, first column of this. First row, second row times the first column gives me the second row, first column of the resulting matrix, and so on. Okay. You may not be used to writing it this way, but this is a much more compact way of writing the same process. So think of this as, or decode this. This is just telling you we're doing matrix multiplication, right? It's saying what we're going to do is sum over J. Now let's think about J. Remember, the first index in that T is row, J is a column index. So sum over all column indices. And notice as we're going across this row here, what's changing is the column index, right? We're in different columns as we go across. and multiply the corresponding element up here times the corresponding element down there. That's what that J repeated there is. And we're going to sum that from 1 to n, and that will tell us what the corresponding position is over here. So it's just a very compact notation that we're going to see again and again. But when you see that, you sort of have to think, oh yeah, that's just matrix multiplication, even though probably in linear algebra, you may not have written it that way. Okay, so that's our familiar context other than writing it as a sum. What about the case where we're representing things in little l2, infinite dimensional vector space with a discrete orthonormal basis, right? That's sort of like our basis vectors are our psi n's from the simple harmonic oscillator, and the components are the cn's. So our components are, we're going to list the components maybe as an infinite column vector, right? Rather than having 6 column vector elements, it will have an infinite number of column vector elements. And not surprisingly, this just transitions into something we might think of as infinite matrix multiplication. If I have, you know, say a linear operator operating on state psi gives me a state beta. The linear operator again is represented by a matrix, but it just never ends. It might have an upper left-hand corner, but it just never ends as you go down and as you go to the right. And similarly, my vectors, of course, I've got an infinite number of these C's, so that vector never ends. But I do the same thing to get the corresponding element over here. If I want to get beta 2, I take the second row of this and multiply by this column to get beta 2. And that's an infinite series. I do have to worry about, oh, is that series going to converge and things like that? Things you don't have to worry about if you're in finite dimensions. A series might diverge, whereas a finite series never diverges, as long as all the things you're multiplying are finite. In any case, the summation kind of formula looks the same in that case. So that's a nice generalization. You know, I remember the first time I realized as an undergraduate, oh yeah, you could do infinite matrix multiplication. That's kind of cool. What about if we're representing our states by functions of a continuous variable? So I might say, remember, if we write our state as a linear combination of maybe we're talking about free particle. So these are the free particle wave functions of which there's a continuum. And if we want to write it as a linear combination of those, then those coefficients g of k are a perfectly valid representation. And I can think of, in that case, as we already discussed, my vector as being a continuous column vector. Instead of having discrete components, I've got a continuum of components there, right? There's g of k prime. And the matrix multiplication then turns into a continuous matrix multiplication. So we got to kind of unpack that a little bit, but I'm drawing a picture here that looks like a regular matrix multiplication, except instead of having discrete entries over here, we've really got a function of 2 variables. This is a function of 1 variable, and it gives us a function of 1 variable. Well, we do the same thing. We take a particular row here and multiply it by a particular column there, and that tells me which element I'm getting over here. We're doing the same thing that we did before, except replacing the sum with integration. So t of k prime times g of k prime, and then integrate with respect to k prime. I'm not sure I see a prime on there, but this should be a k prime index that we're integrating with respect to match the dk prime over there. Okay, I'm not going to say too much about that because actually most of the time, or really every time in this course, when we are going to, if we have a function like a function of x or a function of k, and we have an operator here, we're just going to do the same old things that we've always done, right? Take derivatives, and we already know how to take the derivative as a function of x. The only reason I'm writing it this way is to show that we can make an analogy between these, and you actually can write a function of 2 dimensions, something you can think of as a matrix that represents like a derivative function or the function x, but you have to think hard about it, okay? So that's what this comment is in the notes. In order to represent operators like x and minus I h bar d dx, these functions of two variables, which represent the matrices, have to have things like Dirac delta functions in them, or even derivatives of Dirac delta functions in them. So we're never going to write them that way. I'm only mentioning this to say you can really make the theory look like it's completely analogous as you go from discrete to continuous. But for us, instead of doing this continuous matrix multiplication, we're just going to say, hey, I've got a function of k here, and maybe I've got a derivative with respect to k over here, or I've got a function of x here. And if I've got a derivative with respect to x, or I'm multiplying by x, I just do it the good old way. There is a way to think about it in terms of continuous matrix multiplication, but we're not going to do that in this course. You can do it, and if you're interested in it, maybe I can direct you in the right direction. Okay, so that's talking about how we represent linear operators. You know, just like there are ways to represent, we can represent a vector by a column vector. We represent a linear operator by a matrix, and it can take different guises that way. Now, just to go back to what I've mentioned several times, the reason we're developing this abstract notation for a vector is because we found out from our work in chapter 2 that there are many equivalent ways to represent the information that's in that vector. Okay, the way we started with was at a particular time, you tell me what psi of x is, right? That would be the state at that particular time. That's where everybody starts, like in modern physics. And in modern physics, you're left thinking, well, that's it, you know, that is the state. We don't think of it as a vector, it's a function. But now we're going to say this vector, of course, you know, if I want to write psi as a linear combination of simple harmonic oscillator definite energy states, the coefficients are a perfectly good way to represent that same state. And so we're going to think of that as a different representation. Similarly, if I chose a different potential, here's a quartic potential, I can expand in all of the definite energy states for that, and I get different expansion coefficients. So those would be another way to represent it. And we also discussed in the context of the free particle, I could write psi as a linear combination of 1 over root 2 pi times e to the I kx. And that those coefficients, phi of k, which are called the Fourier transform of psi of x, is another representation. You give me phi of k, hey, this tells me how to build psi of x. So it's just as good as having psi of x, assuming you can do the integral, at least numerically. Okay, this is really analogous to something that we probably don't think about enough in introductory physics, but I've mentioned before. If you have a vector, say in 2 dimensions, it can be represented by its components in a basis or a set of axes, right? So this vector is going to have components vx and vy. But if I take a different set of axes, it's going to have different components. So there are different ways of representing the same vector. There's only one vector, but there are many different representations I might choose. It's the same way up here. All right. Now, one thing to be careful of is that when this may not be worth mentioning, but when mathematicians say a basis, the basis vectors have to be in the vector space itself. If our vector space is capital L2, square integrable functions, then these, what I'm calling the basis functions here, 1 over root 2 pi times e to the I kx, they're not even in capital L2 because they're not square integrable. But we're going to talk about how we can still use them, even though they lie outside the vector space. They're sort of right on the edge of the vector space. We can put a Gaussian envelope over it that's wider and wider, and we'll get closer and closer to those functions within the vector space. They're right on the edge of the vector space. It's worth saying now, giving some words to describe these different representations. These are the big 3 that we're going to use throughout this course. When we write things as a function of x to represent the state of the particle, we call that the position representation because we're writing it as a function of x. And anything having to do with position probabilities is really easy to calculate in that representation. If I write things as a function of, if I give you the expansion coefficients as in front of the definite energy states, we call that the energy representation. If I give you the expansion coefficients in front of the definite momentum states, We call that the momentum representation, or I guess I should really call this the wave number representation, but it's very close to the momentum representation because P is equal to H bar K. They're just proportional to each other. So I could call this the wave number representation, I guess, to be technically correct. Okay. Let's do a worksheet problem just to break things up a little bit. So for those of you on Zoom, this is, I believe I labeled, if you go to our class website and look for the first of the 2 worksheets that are posted for today, I want us to do problem 1, which is just doing stuff that you already knew how to do. So it's good practice from chapter 2, maybe, except that we're using words that weren't introduced until just now. So here's a state, good old Gaussian function, psi of x, normalized Gaussian function. In other words, I'm giving you the position representation of a state. Let's not be so biased about what state you like, how you like to represent the state. I'm giving you the position representation. I didn't have to, but here I am giving you that. And I'm asking you to find the energy representation and the momentum representation for this state. And in the position representation, it happens to be a Gaussian function. Okay, and here we're talking about a particle in the harmonic oscillator potential. You always need to know when you're getting the energy representation what the potential energy function is, because that affects the representation, as we can see on the slide that's up there now. If you choose a different potential, you're going to get a different energy representation, but presumably there's a context of a particle sitting in a potential, and so you know what your potential energy function is. So try problem 1, A and B. We'll do the backside after a little more discussion. I guess I should also mention I'm going to visit somebody else's class right after this, so I can't stay after and talk about homework stuff. If you're desperate to talk about the homework that's nominally due today, we can talk about it on Monday, maybe after class, if you have questions on that. There are the first 4 homework problems from chapter 3. I'm trying to dole them out a little bit at a time as we cover the material. So if you haven't done those yet, certainly try them over the weekend, but I will have to grab my stuff and go really quickly because the classroom I'm going to is in Young. So here in 1, the idea is you could find the all infinite number of these C's one at a time, but why don't you just find C0 and C1 just to get a flavor for how it's going to go. I guess at least on mine, there's one integral that you might want. Oh, I did put it on yours. Okay, it's just not on my solution. Okay, let's finish up the work together. Hopefully at least got started on it. Here's my expression for C0. Remember, what you do is take your state and multiply by the complex conjugate of psi 0 to get C0, and then integrate from minus infinity to infinity. Technically, it needs a star, although this is a real function, so I don't really need to star anything there. And I've got my constant that came with my capital psi. I've got the constant that came with the psi 0. Those come outside the integral. And basically, I've got a Gaussian function, right? It's e to the minus m omega over pi h bar plus a, in parentheses, times x squared. And I look up at my integral up at the top, which I don't have written on this sheet. It's the second integral from the left, that the integral from 0 to infinity of a Gaussian function is a half of that square root of pi over a. In this case, we have an integral from minus infinity to infinity, and it's an even function. So the 1/2 just goes away. So this integral right here is going to be the square root of pi over what I'm calling a in this integral, but that's not the same as this a up here. It's the coefficient of x squared with the minus sign not included in it, right? So that would be m omega over pi h bar plus a, if I'm not mistaken. All of that in the denominator. And that, it's kind of a mess, and I might be able to simplify it with some of the pi's and stuff over here. You can think about that, but it is what it is. It's a bunch of constants there, so we're technically done. Questions on C0? What about C1? Easy. I use symmetry, right? For C1, this is an even function, and this is an even function, but psi 1 star is going to be an odd function, so we'll have an odd integrand, symmetric limits, and so C1 is pretty easy to argue is 0. You could go ahead and use those integrals that I linked to on the homework to figure it out, and you'll find out it's 0, but there's no reason to do it there. Okay, C2 will be non-zero, C3 will be 0, and so on. It's going to alternate. So every other C will be 0 if you bother to go that far. Questions on A? That's the energy representation of the state. There's one state. I gave you the position representation. You're converting it to an energy representation. Now we're going to get the momentum representation, or I guess I should call it the wave number representation. They're so close because P is equal to H bar K, but let's just get phi of K. I guess I should really call it the wave number representation. To do that, the definition was 1 over root 2 pi times your psi of x, which is this function right here, times e to the minus ikx, integrated with respect to x from minus infinity to infinity. And combining these exponential functions in here, I get something that looks like e to the minus ax squared plus ik times x in parentheses. And if you look at the form of the integral in the upper left corner, that means this a is what's called a there, and ik is what's being called b in that integral formula. And therefore, let's see, let's take the constants out in front. I've still got a 1 over root 2 pi times 2a over pi to the 1/4. And then the rest of that integral gives what? The square root of pi over a times e to the b squared over 4a. E to the b squared, b is ik, so b squared is k squared, minus k squared, over 4a. And a in the integral formula is the symbol a here. So I could probably do a lot of simplification there because I've got a's and pi's in several locations. But in any case, it's proportional to e to the minus k squared over 4a. Remember, we sometimes call the magnitude of this the spectrum of the function. And, you know, if you plot the spectrum is going to be peaked around k equals 0, and then it's going to get smaller and smaller for larger k's, right? You could write that as a function of lambda, right? K is 2 pi over lambda, and see how much of each wavelength is included in this. But clearly it is peaked around k equals 0, which means it's peaked around larger wavelengths, because wavelengths and k's are reciprocally related, right? Small k's, same thing as a large lambda. Okay, any questions about that worksheet problem? All right, just, you know, I'm trying to get you used to using the new terminology as we develop it. Okay, so there it is. Position, momentum, energy representation. We're going to be revisiting those as we go through. Now, here's a complication you probably never thought about, and I'm sure you didn't treat it in linear algebra, for those of you who have taken linear algebra here. We're all familiar, like I said on the previous graph, components change when you change basis vectors, right? If I switch which way my x and y axes point, then of course the components that represent the vector are going to change. The same thing is true of the matrix elements that represent a linear operator. Now, in order to see this, or at least give an intuitive sense of that, we got to kind of have an intuition of how to geometrically view a linear operator. And linear operators, sometimes we can think of as they transform space in a certain way. Like if we're in a two-dimensional space, they transform it in a certain way. Here is a linear operator that actually takes things and compresses them by a factor of 1/2 along the vertical dimension, but doesn't do anything in the horizontal direction. So what am I thinking of there? Huh, I thought I had some other slides in here, but I'm not seeing them in here, so that's okay. Maybe I hid them. So maybe I should say a little bit more about that, right? Let me go to the board again. When I think of vectors, you know, I've got this face pictured on there. What is the face about? Well, if I'm in the XY plane and I want to envision what a linear operator does to vectors, right? I could say, well, here's x hat, the vector. Here is y hat, the vector. And maybe when my operator, or the matrix, is applied to the x hat and y hat, perhaps it leaves x hat alone, but y hat gets pushed over here. So here's y hat prime or something like that. Maybe it's not even a unit vector anymore, but that's what it gets transformed to. So in other words, what we would find out is that this point gets mapped to this point, but this point here gets mapped to this point there. That's one way to think of that transformation. And we can do that for lots of different vectors. And what that means is different points in the plane are getting moved to other different points in the plane. And so I can geometrically visualize what it's doing by saying, let me draw an image that covers the plane. And I'm going to take every point in the image and distort the image so that every point where it's supposed to go, that corresponding part of the image gets put over there. So I might say in the plane, and this is the picture I had, here I'll put Mona Lisa's face right there. And if this point goes to over there, and this is where Mona Lisa's nose is, I'm going to draw the tip of Mona Lisa's nose in over here to show how it gets distorted. And what you're going to see is a distorted picture of Mona Lisa's face, but that's going to tell us what happens. And that's what, you know, that very simplified and crude picture of the little box head is showing us. This is saying, hey, a vector, you know, for the box head example, what it's saying is, oh, it looks like this point wouldn't be affected, but this one is going to be sent down here to a vector that looks like this. And so when I visualize a transformation, I can just visualize its effect on a picture, at least if we're talking about the plane, if our vector space is the plane. Obviously, we're not going to be able to do that in an infinite dimensional vector space. Okay, so here is the effect of my transformation. Now, that transformation is going to be very simple in the XY axes. And in fact, I'm going to have you figure out something like that in just a second. But in any case, the transformation in the xy kind of basis vectors that would leave x components alone, but have the y components, that would have a very simple structure for what matrix does that. Now think about in this other basis right here, the x prime, y prime basis. In there, it's not so simple because as that thing gets compressed, we want the physical transformation to be the same, but now you can see as it gets squashed vertically, both the x prime and the y prime components are going to have to change in that case. So all I'm trying to convince you of is there's going to have to be different elements of the matrix that represent it. Okay, so the point is that when I change my representation that I'm using, I'm going to expect that my representation of the operators, and if I'm representing them by matrices, those matrix elements are going to change too, which makes it seem very complicated. And we'll practice a lot with that later on. For right now, I want you to do this, the back page of the worksheet, which is talking exactly about this transformation. And I'm asking you to find the matrix elements of the transformation that affects this in the XY axes. And if you really had time, if I wanted to give you 15 minutes to work on it, you could probably figure out what it does in the X prime, Y prime axes too. It's not too complicated, but it might be a little bit disorienting. What you're supposed to do in A is figure out what matrix elements, those 4 matrix elements in a 2x2 matrix, that would affect this vertical squashing by a factor of half, but not affecting the horizontal width as matrix elements. And then I'm asking for in B just a sentence that describes how you could be convinced that the matrix elements are definitely not going to be the same if you use the X prime, Y prime axes. And you'll see that later on, I believe at the end of this chapter, we'll practice much more with changing matrix elements as we go to different representations. I'm not going to give you too long to work on this one because you may find it really easy. Okay, some are sitting as if they're done, at least in the classroom here. So let's talk about it together. Here's an arbitrary vector in the XY plane. We're talking about, we want to get a representation by matrix elements in this basis, the X hat, Y hat basis, that represents the process of transforming things so that they get squashed towards the X axis by a factor of 1/2, but nothing happens horizontally. So if I take just as an example, this vector V here, which is pointing in an arbitrary direction, where's it going to get transformed to by that process? Well, this point should go down to this point right here that has half the y coordinate, which means this vector is going to get transformed to this vector. This is going to be a picture of T acting on V, right? Now this vector has the first one here, maybe I need colored chalk. This bigger vector, the initial one, has components Vx, which looks like this, and Vy, which is the length of this side, right? And so it looks like if I start with a vector x Vy, it should get transformed under the action of t to Vx 1/2 Vy, right? Or 0.5 times Vy. And so the only question is, I want to figure out some matrix elements that do this. And it's pretty simple to do that. Vx 0.5 Vy. What needs to go here? Okay. 1, 0, 0, 1/2. And you know, you can do your matrix multiplication and show that it does that. So that's a representation of that transformation. And I've just shown that if it can be represented by a matrix, it's a linear transformation. There are a lot of transformations you could think of that aren't representable by matrices. They wouldn't be linear transformations. Okay, so that's one way to represent what this operator is by matrix elements in a particular representation or a particular basis, x hat, y hat basis. The matrix elements are going to change when you go to the x prime, y prime axes. That's a different representation. And that's pretty clear because when I squash in this direction, I'm going to change both the x and y components. And at least with this kind of matrix, you can see the x component's always going to stay the same and the y component does the changing. In the other tilted axes, both components are going to change. So it can't have the same kind of matrix elements. It's got to have some, well, you can think about it, but the point is that we need to change those. Questions on that? Okay. Now we're finally getting back to, you know, something that you read about. A lot of the stuff is just sort of side comments, but we're now heading into 3.2 or the main points of 3.2. What are the special properties of operators associated with dynamical variables, right? So we've been talking about operators. We could make all kinds of operators, but we're in particular interested in ones associated with the dynamical variables. X, position, momentum, energy, potential energy, kinetic energy. Those are the big ones, right, that we use to describe things in classical mechanics. Can any operator represent a dynamical variable? No, we're going to find out that that's not the case because when we measure a dynamical variable, we have to get a real variable outcome. These matrix elements don't have to have real numbers in them, but they have to correspond to, when we make a measurement, we get a real variable outcome. And one thing that means, if every time we make a measurement, we get a real variable outcome, that means the expectation value of a particular operator has to be a real number, right? You can't get the expectation value of position is 3i. Nobody knows what that means, right? Every measurement has to have a real outcome. Okay, so along that way, we're going to make this definition of a Hermitian operator, which I'm assuming you didn't talk about in modern physics. You don't talk about Hermitian operators much at all, I bet. Okay, so for right now, just take this definition as what it is. Okay, so here's an operator. It's Hermitian if I take the inner product of F with QF, or more generally of G with Q acting on F. And, you know, again, you might say, what is that vector QF? I guess it's worth mentioning here that, again, when we label an abstract vector like this, I've made up a label. Just like, you know, I could call a vector A with a vector symbol over it. You know, you can choose whatever symbol you want. Here I've made sort of a complicated symbol. And it's supposed to be reminding me that this is a vector that results from letting this operator act on the vector F. I mean, I can make up my own notation, and sometimes I choose notation like this, and this is common in quantum mechanics to denote something like this. When you write it like this, It means it's what results from this. And it's just supposed to remind you of that. It's sort of a complicated label for it. Okay, so a Hermitian operator is one that if I take the inner product with the, of a vector with itself multiple with Q operating on it, then it's equal to the same thing as the inner product run the other way. Or more generally, this is usually what you see in other textbooks, but this is actually what Griffith says here. If you have two different vectors, F and G, you can take that operator and move it over to the other side, and you get the same result. Okay? And it turns out it's exactly these Hermitian operators that are going to have real outcomes associated with measurements. They're going to have real expectation values and so on, right? Everything about them is going to be real. That doesn't mean their matrix elements will be real, but they will have real outcomes. Okay? You've got to figure out how to unpack this. And on the way to doing that, we're going to do some worksheet problems to practice with this. Okay? So the claim is that I guess I shouldn't say therefore here. We haven't proved this. This is going to be the result of a theorem, but physical observables are going to be represented by Hermitian operators, and we will show later on that you always get a real expectation value, and that if you make a measurement, you're always going to get a real outcome for that measurement. Whereas if you just make up a random operator, you might get a complex output for your measurement or for your expectation value when you compute it. Okay. Here's another definition that's related. Not all operators have that special property that when you move them from one side of an inner product to the other, you get the same result. Usually, in order for these two to be equal, you're going to have to change the operator when you move it from the the right side over to the left side. And we'll see what this means in just a second. More generally, if you have any old operator, we're not going to call it a Hermitian operator. It could be an operator that doesn't represent a dynamical variable. And to be something like the raising and lowering operators that we've seen before. Those are not Hermitian operators. It's not at all obvious without doing some work to show it. We can say if that operator is in an inner product here like this, if you move it to the other side of the inner product, it's a different operator in general. And that means we're going to call that different operator that's on the other side of the inner product the Hermitian conjugate of that operator. Okay? And therefore, it follows that if an operator is Hermitian, we can call it self-adjoint. In other words, it is equal to its Hermitian conjugate. So the Hermitian conjugate is just whatever it has to be to go to the other side. Let me do an example of this. I wonder if I have one in the notes here, because I don't think there are any in the slides, but maybe we could do it on the board. No, I have a note saying we're supposed to do a worksheet, but it's probably best to do an example on the board first. So let's find the Hermitian conjugate, or sometimes called the adjoint of this operator. And here, let me just define an operator. My operator, well, let's do two operators. First, let's do X. That's a nice simple one. The operator who in the position representation, it just means multiply by X. Okay, so what we're going to do is start with the inner product of some state with our operator operating on another state, okay? And I'm going to work in the position representation, so I'm going to say our vector f, it will be represented, of course, by a function f of x, and our vector g will be represented, of course, by a function g of x, and our operator that I'm going to choose is going to be represented in the position representation by just multiplication by x. It's the usual old position operator, okay? So what I'm going to do is now decode this into our usual representation of the inner product. This means in the position representation, integrate from minus infinity to infinity. The thing on the left gets a star, right, on its corresponding function. And then this vector, this would be g of x. The operator O operating on g of x is just, the result is x times g of x. That's what O times G is there. And then we're supposed to integrate. All right. Somehow I've got to move this operator over to the other side. So I've got to manipulate that and say that's equal to, after some manipulation, some other operator. We put a little dagger superscript on it. That dagger superscript means the Hermitian conjugate or adjoint. Operating on F, inner product with G. That means I need to somehow get this operator over on the F. Now, because it's just multiplication by X, I can move the X anywhere under the integrand. There's no derivatives that I'm moving through, so it seems okay there. But I also have to get it under that star, right? So certainly taking the X and moving it over there, there's no problem. Now, here's a question. Can I do this? I put, originally I just had the star and the F. Now I put the X under the star. And the answer is yes. Why are you saying yes, Yichen? X is always real. Remember, our functions can have complex outputs, but X itself is the real number line axis. So for us, X is always real. And therefore, X, when you take the complex conjugate of a product of functions, that's the same thing as the product of the individual complex conjugate. So, if I really wanted to be step by step, I could say, well, X is equal to X star, and then I could put them both under the star like that. And therefore, I'm looking at what's under the star and saying, this is the position representation of O dagger. And O dagger is equal to O in this case. So we would say the position operator is a Hermitian operator because it equals its adjoint. I know that's a lot of words for a very simple kind of concept. Let's move to a different example. Got to keep an eye on the time so I'm not late to my other class. What about if I just say, I'm not interested in this one. Let's put an I in front of the X. Just making up an operator. Let's see if it's Hermitian. Let's find out what its adjoint is or its Hermitian conjugate. How does the argument change? Well, okay. So here was my X sitting here, but it's now got an I next to it, right? That's IX operating on G of X just multiplies it by IX in this position representation, okay? How do I get this underneath there and just leave only the G of X by itself? Well, I move the X underneath. It doesn't care. What happens when I move the I underneath? I didn't leave myself enough room here.
Turns negative?
Yeah, it turns into a minus I. So that means in this case, what I figured out is that O dagger, the Hermitian conjugate of this operator, is in the position representation minus IX. And so IX is not a Hermitian operator. Once we get to the theorem about this, we're not going to expect this operator to have, if you measure a value of this, you wouldn't expect a real output. So we wouldn't expect it to correspond to a measurement at all. Usually when we measure anything, we're expecting a real output. The expectation value of this operator might give something imaginary, and that would be confusing if we were thinking of it as something we're actually going to measure. So it doesn't represent a real measurable quantity like position, momentum, energy. Okay. Here's the next one on the worksheet, and you can let's just start thinking about how we might deal with it. That's almost the momentum operator. It's missing a minus IH bar in front of it, right? Or at least we would now call that the position representation of momentum operator. What's going to happen here? I know my thing's getting kind of messed up here from all my erasing, but originally this inner product right here is going to look like this. The derivative operator operating on g of x is what belongs in this position. Now, how in the world am I going to get that derivative operator over on this side and off the g of x? That's something you've done in math classes before and in physics classes, I know. What's the process called of getting a derivative off of one thing in an integrand and getting it over to the other thing in the integrand? That's called integration by parts, right? If you have, you know, the integral of f times dg dx under an integral, you could say that's equal to minus the integral of the derivative of f with respect to x times g, but I also need a boundary term. The boundary term is f of x times g of x evaluated between the two limits, right? So if I'm integrating from minus infinity to infinity, I'd have to do that. That's what integration by parts means. So that's how we're going to do this to get this over here. And we will find out, we'll do these worksheet examples at the beginning of Monday. We'll find out this is not a Hermitian operator. It gets an extra minus sign when you do that. And that minus sign is just coming from this part of integration by parts right here. But if I put an I in front of it, then it is a Hermitian operator. And that's, you know, and if I also put a minus h bar in front of it, that doesn't affect anything because the minus h bar can move underneath a star. And this is the momentum operator. So we're going to find without an I in there, it wouldn't be Hermitian. You need that I in there in order for it to represent a real measurable quantity. Okay,